Thanks for the introduction. So I'll talk about Hoare logic, a program logic to prove and disprove hyperproperties. So here, what are hyperproperties and why should we care about them? So the usual definition of a hyperproperty is that this is a property of a set of executions. And to give an example, non-interference is an important security property that says that public outputs are only influenced by public inputs and not by secret inputs. So more formally, it says that for any two executions, if they have the same public inputs, then they must have the same public outputs. So these hyperproperties universally quantify over pairs of two executions. So this is also called the two-safety hyperproperties. And there are many other two-safety hyperproperties, such as determinism. Two executions with the same inputs should result in the same outputs, or monotonicity. Monotonicity is two-safety because intuitively it compares two runs of the same execution. There are also k-safety hyperproperties for more than two executions. One example is transitivity, because again, intuitively it compares three executions of this, three runs of the same program. Or functional correctness only cares about single executions. But we also have hyperproperties that existentially quantify over executions. So reachability is one example, either reachability of some good outcome or reachability of a bug a la incorrectness logic. And there are hyperproperties that combine universal and existential quantification. So generalized non-interference, which is a relaxation of non-interference for non-deterministic programs, or the existence of a minimum. And if we are interested in violation of those properties or proving that those properties do not hold, their negations are also hyperproperties, where their type is obtained by flipping the universal and existential quantifiers. So to give an example, to prove that a function is not monotonic, we need to prove the existence of two executions where f flips the order of x and y. So hyperproperties, many important properties, functional and security, are hyperproperties. And so our goal in this work was to develop the first program logic that can handle all the different types of hyperproperties shown in this slide. So our main contribution is Hoare logic, a program logic that allows to prove and disprove program hyperproperties, which includes all the hyperproperties on the previous slide. And so more precisely, Hoare logic establishes hypertriples, triples where preconditions and postconditions are assertions over sets of states. And in this work, we show that those hypertriples are highly expressive. So they capture exactly the class of program hyperproperties, properties over sets of terminating executions. But we also relate hypertriples to many existing judgments of existing hyperlogics and Hoare logics in general. We also provide many inference rules to establish such hypertriples. So we first provide a minimal set of core rules for which we prove soundness and completeness. But while those rules are complete, they're not always the most convenient rules to use. And so we also present many additional inference rules, such as syntactic rules, better rules to handle different types of loops, and compositionality rules. So rules that allow composing, for example, for all hyperproperties with exist for all hyperproperties, such as composing a function that is monotonic with a one that has a minimum. So in the rest of everything in this work has been formalized and proven in the Isabelle Proof Assistant. And in the rest of this talk, I'm going to introduce hypertriples, talk a bit about their expressivity, and then present briefly core and syntactic rules. So our triples, unlike in the previous talk, talk only about one program in the middle. But the key idea compared to related work is that P and Q are assertions over sets of states. And so their definition is the definition of the validity of a hypertriple is rather straightforward. And this is like the standard Hoare logic triples. So it says that given any set S of initial states that satisfies the precondition P, the set of states reachable by executing C in any state from S should satisfy the postcondition. So this is a bit of a mouthful. So formally, this set is expressed like this, but I want to show it more visually. So we start with a set of initial states here where each dot represents one initial state. And we want to construct this set of reachable states. So if we take this first initial state and we execute C, maybe for this state the execution is deterministic, we get one final state. This final state is in our set of reachable states. But we can have also non-determinism. In this case, we might get, for one initial state, 3 final states. We collect the 3 states here. And we might also have states, executions that do not terminate. And we don't have a final state in this case, so we simply do not collect anything. So this is the core of Hoare logic, those hypertriples. But how can we use them to express hyperproperties, as I've shown before? So if we want to express non-interference, where we assume our public input to be the variable x and our public output y, we can express them like this. So here we use some notation, some syntactic sugar. So these angle brackets mean that sigma 1 and sigma 2 are part of the set S. So this precondition can be seen as all pairs of states here have the same value for x, or equivalently, all the states have the same value for x. And so the postcondition says the same. So this triple together says that if all initial states have the same value for x, then all final states will have the same value for y. This this expresses exactly non-interference. But if we want to express properties like monotonicity, for example, we have to do a bit more work. So we would like to express monotonicity with the same syntactic notation and in a similar way by saying that given any 2 states, we have a sigma 1 that is strictly greater than sigma 2, but this hypertriple would not express monotonicity because sigma 1 and sigma 2 can be instantiated to the same state, and this is not a reflexive nor symmetric condition. So this precondition would be only satisfiable by the empty set. So we need a way to distinguish which execution is intuitively our first execution and which one is our second one. And so we do that by employing what we call logical variables, or here a logical tag. So the key part is that t, the variable t here, does not influence the program C. And so we can think about this as dividing our states in our set of states into green states where t equals 2 and orange states where t equals 1. There might be other value for t, but here that does not matter. And then, as I said, the key part is that those tags are going to be preserved by the execution. So when we are in the postcondition here, we can refer to these tags. We can know which executions was the first one and which was the second one. And so this triple here says that if all initial orange states have a larger value than all green states, so notice that we do not express any relation between the orange states, then all the final orange states have a larger value for y than all green states. And this way of expressing 2 safety hyperproperties is a general way for which we can encode relational Hoare logic triples. But no, that's what other logics could do. But because we have sets of states, we can express arbitrary properties over this set. So we can express, for example, the existence of a minimal state after the execution. So we can say, using the same notation, that there exists a state sigma that has a smaller value for x and y than all other states. So visually, this state is here, and it has a smaller value than all the other ones. And so for this postcondition to be satisfiable, we need our final set of states to be non-empty. And so our postcondition here can simply be that the set of initial states is also non-empty. If we had an empty set of initial states, then we would have no reachable states, and so the set here would also be empty. So that's how we can express different types of hyperproperties. But more generally, we looked at the judgments of existing, there are many existing logics to reason about hyperproperties. So we look at their judgments that we restricted in some cases to a single non-deterministic program, which is the one that Hoare logic covers. And we obtained more or less the following pictures. So the reason why we have to restrict those judgments to a single program is because logics like relational Hoare logic, for example, have 2 programs in their judgments, and so they can express properties relating multiple executions of different programs, like in the previous talk also. And in general, we characterize the types of properties that those logics can establish, and there is much more. There is more in the paper. So now that we've seen that hypertriples are really expressive, the question is how can we establish them? So as I said, we first present a first set of core rules, a minimal set for which we can obtain soundness and completeness. So these core rules are formalized for the following imperative non-deterministic programming language, where we have a non-deterministic assignment. We have an assume statement. So if you're not familiar with this, this statement will stop an execution where B does not hold, but if B holds, this is like a skip. And we use a non-deterministic choice and a non-deterministic iteration. The reason is this is more general than conditionals and while loops, because they can be recovered with those primitives. And so we provide 9 core rules that can be roughly split into 3 categories. So we have 4 what we call standard rules, because they are basically the same as in normal Hoare logic. So for example, we have the usual sequential composition rule that says if the postcondition R of our first triple matches the precondition of our second triple, then we can sequentially compose them together. What is interesting here is that we have this rule exist that allows us to introduce an existential quantifier in the pre and the post condition of a triple, and this is actually required for completeness, and we show why in the paper. Then we have 2 rules for branching, so for non-deterministic choice and non-deterministic iteration. Those rules are a bit less standard. So this rule says that if we can obtain a set of states that satisfy Q1 by executing C1 in a set of states that satisfies P, and the same for C2 and Q2, after executing C1 plus C2, so this is a non-deterministic choice. It means we non-deterministically execute either C1 or C2. We will obtain a set of states that can be seen as the union of a set S1 that satisfies Q1 and a set S2 that satisfies Q2. And finally, we have 3 atomic rules for atomic statements, so deterministic and non-deterministic assignments and assume statements that look like this. So they look a bit complicated, but mostly this is just the weakest precondition rule. So we take an arbitrary semantic postcondition here, P, and this precondition is simply saying P should hold of the set of states we will obtain. So those 3 atomic rules are necessary to obtain completeness, but they're a bit inconvenient to use in practice. And so we show that for a large set of syntactic hyperassertions, we can see those rules are syntactic transformation. So this one as a syntactic substitution. So we define the following grammar for hyperassertions. The key point are those 2 quantifiers here. We restrict the interaction with the set of states to only universal and existential quantifiers. And as I've shown you in the examples that we've seen, this is enough to express the hyperproperties we want, and this is enough to express many existing judgments. And so how do we use those rules? So if we want to establish the following triple, if there exists an initial state alpha with r equals 0 and that has a minimal value for x, we would like to prove that at the end we will have a final state alpha with minimal values for both x and y. So here we first look at the assignment, and for an assignment our rule is a generalization of the standard Hoare logic rule that is based on substitution. So we assign to y, and we have alpha of y and sigma of y in our post condition. So we will simply do a syntactic substitution for each. So we replace alpha of y by alpha of x plus alpha of r, because this is what the assignment is. And this is a general rule. We look at all the quantified states in our hyperassertion, and we apply this syntactic substitution. So now we need to reason about this assume statement. So assume, recall, stops the execution if B does not hold. And here we look at the quantifiers. So we have a state that is existentially quantified and a state that is universally quantified. And so for the existentially quantified state, to prove that it exists after the assume, we need to prove that it existed before the assume and it satisfies the condition. So it will not stop its execution with the assume. So this can be thought of as a proof obligation. Whereas for the universal quantifier, here we only care about the states that are going to survive the assume. So we can assume, we can see this condition as an assumption. And the rest of the assertion is unchanged. So this is the general way the general rule to obtain a precondition for assume. And there is a similar syntactic rule for a non-deterministic assignment. And we can finally conclude by using the consequence rule. So to conclude, I've shown you, I've presented Hoare logic, which establishes hypertriples. So the key idea is to track sets of states. In the paper, we show much more. So we show that those triples are highly expressive, and we show, in particular, inference rules for loops and for compositionality. And we are working on automating, on building a deductive verifier based on Hoare logic. And we want to extend Hoare logic to relational properties, so more than one program, as in the previous talk, and to heap manipulating programs. So thank you for your attention, and I'm happy to take any questions.
Thanks, Thibault. Very interesting work. So my question is, so it's very nice to have this unifying theory. Do you have examples of things you can do with this that you can't do with any of the existing logics, or that rely on some composition of principles from existing logics?
Yes, so that's a good question that I haven't really covered here. So the first one, I'm not sure if it's visible on this diagram, is that there were not really logics that provide inference rules for exist star for all star properties, or exist star where you have more than 2 executions. So that's one thing where we get additional expressivities for this. But then we also have examples. So RH Shelley, for example, can do for all star exist star hyperproperties. But our loop rules, some of our loop rules are actually more general than the loop rules that are there. So that, and a third point is that when we actually do proofs, it turns out that it's really convenient to be able to say, okay, I want this. For example, when writing a loop invariant, I want a relational part, says that compare 2 states, but I also want a part that is for every single execution, right? So that we don't have to duplicate things. So there is, that we have several examples in the paper that show those different benefits.
Okay,
thanks. You've showed us many hard triples referring to explicit states in the encodings. But in separation logic, it is not something you typically do. So how would you see similar encodings in separation logic?
So you mean how? So the one thing I can so we have been looking with another student at extending it to, in a sense, a separation logic version, and this is the long story short is that there are many challenges. As you point out, there are one big challenge that is maybe not even that, but is that. So one big challenge is to define what it means to have a separation conjunction between different hyperassertions. But another one is that the typical way you would like to write your specification is maybe you have a for all property that gives you ownership, and then you star it, and in the you might want to express something like this, where the ownership has been described before. So here we can borrow ideas from implicit dynamic frames, for example, where the ownership is justified at one place and the values are justified at another place. I don't know if that answers your question. We can take it offline.
Let's take one last question while the next speaker sets up.
Not sure if you already covered this. Sorry if this is a repetition. Can you tell me what the statement of your completeness is? You said the logic is sound and complete. What is the completeness?
Yes, so it says that for any valid hypertriple, semantic, so any precondition and postcondition that is valid according to the definition I gave, can be proven using the core rules.
And it depends on your programming language essentially being encodable by your logic. Because for the loop...
No, so the loop rule that I haven't shown is this is the same type of completeness argument as in standard Hoare logic. The rule allows you to describe exactly what happens at every. So it's more a completeness statement in the sense that no rule is missing, but it doesn't mean that the loop rule in the core rule is good, right? It's really the typical argument where you say I can exactly express my set of states.
Your logic is powerful enough to describe the set of reachable states.
Yes, but that's not how you would like to use it in practice, right?
Sure.
You want abstraction, but yes, that's.
Great. Thank you very much.